Hi, I'm Peitong. I'm a fourth-year PhD student at Berkeley. I worked on this project with Jeremy Warner, Yang Li, and my advisor Bjoern Hartmann. Feedback is essential for the UI design process, and design feedback has traditionally come from humans via user studies and expert evaluations. However, human feedback is not always readily available. Recent advances in computational UI design enable instantaneous automatic feedback. However, this automated feedback is not generalizable and can be difficult to interpret. For example, recent work in automated UI evaluation and optimization include a design tool that uses autoencoders and CNNs to provide feedback at various stages of the design process, applying the gradients of a trained task performance model to optimize the input layout for predicted task performance, and using computer vision techniques to predict perceived tappability. However, each of these techniques require large amounts of training to carry out a single task and are unable to generalize. Also, their user studies revealed that participants sometimes found the model's feedback hard to interpret and preferred natural language explanations. The recent rise of large language models, such as GPT, showcase strong generalization and reasoning abilities, which have led to their use in design support. Existing studies include using LLMs to generate synthetic user responses to surveys about video game experiences and to help create functional LLM-based UI prototypes. These existing studies have not yet leveraged LLM's generalization and reasoning abilities as a general-purpose evaluator of UI designs. One common method for UI evaluation that still relies on human participants today is heuristic evaluation, when an experienced human designer applies a set of text-based rules to identify and describe violations in the UI. LLMs show promise for automating this task. They can generalize to accommodate arbitrary heuristics in UIs and demonstrated capacity to carry out rule-based reasoning, which is a big part of heuristic evaluation. Also, design guidelines are mainly in text form, making them amenable to LLMs. And large language models can return feedback as text-based explanations that designers prefer. However, there are also reasons for caution when using LLMs for this task. LLMs only process text at a time, while UIs are complex artifacts that consist of images, text, and UI components. And LLMs have been known to hallucinate and might generate false guideline violations. We explore the potential of using large language models to automatically carry out heuristic evaluation. In particular, we aim to determine their performance, strengths and limitations, and how an LLM-based tool can fit into existing design practices. To study this, we first built a plugin for Figma, a popular design tool. Designers can run this plugin to carry out LLM-driven heuristic evaluation to automatically evaluate their mockups. Results from the heuristic evaluation are rendered within the Figma plugin and are contextualized within the UI. The designer will then use to identify guideline violations to revise their mockup and then repeat this process. We will show a quick demo video that illustrates some of the plugin's features.
Let's say the designer has finished mocking up their UI. To run the evaluation, the designer would first select the entire mockup and then run the plugin. The plugin opens the page where they can select from a list of popular guidelines, such as the Nielsen-Norman 10 usability heuristics. There's also an option for designers to enter in custom guidelines they wish to use. Let's say the designer selects the Nielsen-Norman 10 usability heuristics. They can select more than one set of guidelines at a time. Here are the evaluation results. There are violation explanations on the left and boxes drawn around corresponding groups on the screenshot on the right. The violations are ordered by their usability severity ratings that are also generated by the LLM. The designer can click on a violation to focus on it, which fades out all the other violations and irrelevant boxes in the screenshot. The violation explanations are phrased in a constructive manner as suggestions to improve the design. Another feature to help contextualize the violations within the UI is that the designer can hover over UI elements and groups mentioned in the violation text, and it will draw a blue box over the items in the screenshot. And clicking on these links will select the item in the Figma mockup and layers panel. Let's look at a few violations. This one is saying that the product price appears twice in the interface, which is confusing, and it's true. This one is saying that there should be a way for users to interact with the reviews, like viewing more or adding their own review, which is a great suggestion. For incorrect suggestions like this one, the designer can click on the X button to hide it, and this feedback will be sent to the LLM to improve its performance for the next round of evaluation.
Since LLMs could only accept text input at a time, we use the JSON representation of the UI mockup shown on the right, which is available via the Figma plugin API. This JSON structure is similar to the DOM representation, which models the UI as a tree structure with UI elements as leaves and groups as intermediate nodes. This slide shows corresponding groups and elements marked in the JSON in the screenshot on the left. As you can see, this JSON representation captures both visual and semantic information about the UI. We implemented this plugin using the Figma plugin API. The plugin code first takes in and compresses the mockups JSON representation and constructs a prompt consisting of this and the text of the selected heuristics. The plugin then queries the LLM, parses the results, and generates an interpretable representation for the designer. Feedback from the designer is incorporated into future prompts to the LLM. We explored various prompt compositions and found that this design maximizes performance. The first prompt queries the LLM to execute the heuristic evaluation, which consists of the task description and heuristics text, followed by the conversation history of incorrect violations marked by the designer, and then the UI JSON. The response from this prompt is then passed into a second prompt, asking the LLM to rephrase violations as constructive design feedback. Since UI JSONs are quite long, there's not enough room in the LLM's context window at the time to incorporate additional performance-enhancing features, such as few-shot prompting. We also investigated the performance of various state-of-the-art LLMs and found that GPT-4 had the best performance by far. Hence, we solely focused on GPT-4 for subsequent studies. We carried out 3 studies to explore the potential of GPT-4 in automating heuristic evaluation. To obtain quantitative metrics of the LLM's performance, we ran a large-scale study where 3 designers evaluated the accuracy and helpfulness of LLM-identified violations across 51 UIs. We used 3 sets of guidelines: the Nielsen-Norman 10 usability heuristics, the CrowdCrit visual design critiques, and a set of semantic grouping guidelines. Overall, GPT-4 provided helpful suggestions around 60% of the time, and here's a histogram showing the numerical ratings for accuracy and helpfulness, broken down by each set of heuristics. We see that the LLM had the best performance for the CrowdCrit visual design critiques, probably because a lot of its heuristics consist of straightforward numerical checks like contrast and alignment. To compare GPT-4's performance with human experts, we next conducted a study where 12 design experts manually performed heuristic evaluation, and we compared their annotations with those identified by the LLM. We built a ground truth dataset consisting of these human-identified violations and expert-validated LLM comments from a prior study. We then computed the precision recall and F1 scores for GPT-4 and an individual human evaluator. We found that they had comparable F1 scores, but a human evaluator greatly outperformed GPT-4 in precision, meaning their identified violations are more likely to be valid, while GPT-4 had higher recall, meaning it found more valid violations. Qualitative analysis revealed that humans found more global or high-level violations requiring a comprehensive understanding of the UI context, and also violations requiring advanced visual understanding of the UI. Whereas GPT-4 was more specific and found more detailed and easy to miss errors. Here's an example comparing a global human-identified violation with a similar but more specific one found by GPT-4. The LLM comment, labeled L1, suggests clarifying the swipe up for details text label by specifying what details will be revealed after swiping up this large photo. While the human evaluator's broader comment states that a lot of important details are hidden behind this large image, which adds to the user's memory load. Finally, in the iterative usage study, we asked 12 design experts to iteratively obtain LLM suggestions, evaluate their accuracy and helpfulness with justification, and follow valid design suggestions to edit the mockup. We concluded this study with an interview about the participants' experience with the tool. We visualized the accuracy and helpfulness ratings as histograms, and as you can see from the average ratings, the performance generally became worse per round. One explanation for this is that when the design experts implements the LLM's valid suggestions, the UI design becomes better with each iteration. And when there are fewer design issues to find, this task becomes harder for the LLM, causing it to return more invalid suggestions. This slide shows the state of the mockup at each iteration. You can see the design improving as the participant fixes design issues, which are highlighted in the screenshot. This result implies that this tool may not be ready for iterative usage yet. Through qualitative analysis of ratings, explanations, and interviews, we distilled a set of GPT-4's strengths and weaknesses for this task. Its strengths include detecting subtle violations that are difficult to find, such as slight misalignment, resolving text-related issues, such as confusing text labels, and reasoning with the UI semantics, such as identifying menus with unrelated items. Here's an example of a GPT-4 violation that was highly rated by all participants, which illustrates its strength in identifying subtle violations. But the contact field is slightly misaligned with the name and location fields, which was caught by the LLM. Here's an example of a highly rated violation regarding the UI semantics, which says that items in the menu are not that related and could be subgrouped into more related categories. GPT-4's weaknesses include over-application of the guideline, where the LLM applied the guideline too literally and ignored broader UI context and popular design conventions. Limitations of using JSON to represent the UI, which presents issues when there is a mismatch between the JSON and what is shown visually in the UI. And finally, GPT-4 sometimes gave vague suggestions on how to fix the violation. Here's an example of a poorly rated GPT-4 violation. The LLM is stating that it violates consistency, as the line thickness under the two tabs is not the same. This is an over-application of the consistency guideline, as this uneven line thickness is meant to convey the selected tab in the broader context of the UI. Another bad LLM suggestion claimed that these images overlap when they do not overlap visually. Their bounding boxes in the UI JSON probably overlap, which caused GPT-4 to output this violation. We analyzed interview results to investigate this tool's fit into existing design practice. 9 out of 12 participants said they will use this tool, and they will use it for things like assisting in the exploration of early-stage concepts and low-fidelity prototypes, and evaluating their high-fidelity mockups. Participants also brainstormed potential use cases for this tool, which includes saving time on busy work like alignment checks, getting a second opinion on their design, which is useful for designers working solo, and running accessibility checks via applying accessibility guidelines. Regarding mistakes made by GPT-4, 8 out of 12 participants said they are not dangerous, as there's a human in the loop to catch these mistakes before UI revisions. However, some noted that these errors could be dangerous to novice designers. Key insights from these studies are that despite current limitations, LLMs are able to apply some heuristics for reasonable accuracy, while others require more visual information or other technical advancements. And designers were accepting of occasional imperfect suggestions and appreciated the LLM's attention to detail and its other strengths. This means that while LLMs will now replace human heuristic evaluation, they will likely become a valuable addition to design practice. So this research opens up exciting opportunities for future work. The recent emergence of multimodal LLMs such as GPT-4v and those with larger context windows enable studies on the performance with UI screenshots as input and also few-shot training. We also released the dataset collected from the performance study. Another direction could be to fine-tune an LLM to see if it addresses the weaknesses we found. Finally, with improved performance, it will be exciting to run a study where designers use this tool to create a design from a prompt to measure its effect on design outcome. Thank you for listening.